All right, folks, so today in class, I introduce you to the idea of equilibrium. You may recall me discussing how in a beehive, the total number of bees inside and out of the hive remain constant, but it doesn't mean that individual bees aren't moving inside and outside of that hive. So that is sort of like what happens in equilibrium. It's not as though the molecules are staying as products or staying as reactants. The relative amounts of product and reactant remain constant, but molecules are constantly forming product and reforming reactant if we're looking at an equilibrium system. So not all reactions are going to proceed from beginning to end to produce products. Some are going to actually happen in the reverse direction as well, which is why we've indicated that using the double-headed arrow. So we're going to come back to the rest of note number 1 tomorrow in class because it's a little bit more complicated. I'd like to do that together. So we're going to move on to note number 2, where I'm going to discuss with you some basic ideas around equilibrium, like where will you see equilibrium, what types of equilibria are there in the world, and so on and so forth. So the first type of equilibrium exists between the liquid phase and the gas phase. So sometimes that's referred to as a vapor-liquid equilibrium. So what I want you to imagine is that this bottle of water is about half full, and that you are just about to leave it somewhere where it's going to be in front of some direct sunlight. So at the very beginning, at the moment that you leave this in front of, a window, let's say, where the sun is shining on it, all of the water in that bottle will be in the liquid phase or the liquid state. So, but as the sunlight shines upon that water, those water molecules in here are going to gain energy. And some of those water molecules are going to gain enough energy so that they begin to become gas molecules or water vapor. So there's a period before this system reaches equilibrium where the water molecules are all in the liquid state, and we're not seeing this reaction happen in reverse. Only the forward reaction occurs. So in other words, we're only going to see at the very beginning of this reaction the liquid water form water vapor. We're not going to see any water vapor reform reactants. And the reason for that is that we don't have any a substantial amount of water vapor molecules in order to reform reactants for us. So the forward reaction, we say, is much, much faster. However, there comes a point during the reaction where you have enough of these water vapor molecules floating around in the area above the liquid water. And you can see signified in this diagram, but there are some water molecules that are vapor that are going to go back and reform liquid water. They're going to condense. And for every one water molecule that's in the vapor form that reforms and condenses into liquid water, we see one liquid water molecule evaporate to become water vapor. So at that point, we see that the rate of evaporation is equal to the rate of condensation. And so this particular system has reached equilibrium. Another thing to notice is that in this example that I've used, in all of these diagrams, you'll see that this is a closed system. I've put a stopper on this flask so that the gas molecules, the water vapor molecules, can't escape. So one particular point that needs to be true of a system in equilibrium, it needs to be closed. Sort of like if you were leaving your clothes in the dryer at home and the dryer door were closed, your clothes would stay nice and wet for a while, or in the washing machine for that matter. However, if you were to open the door of the washing machine or the dryer with wet clothes in it, over a certain amount of time you would see that your clothing would become drier and drier. Okay, so the first example where the door to the dryer or washer is shut is an example of a closed system, and we're going to see this type of equilibrium happen where the water vapor and the liquid water are going to remain in equilibrium because there's nowhere for those water vapor molecules to go. However, if the door to the machine is open, then the water vapor can escape, and that will never reach equilibrium. So what you need to know is that this type of equilibrium has a special name. It's referred to as phase equilibrium. So phase is another word for state of matter, so the phase or the layer. What we mean by this is that we have the two reactants in the gas phase and in the liquid phase interacting with each other and reaching an equilibrium. Alright, so the second type of equilibrium that you might run into is an equilibrium existing between a solid that you want to dissolve in some kind of a solvent. So I'm going to use the example of water because water is our universal solvent and is able to dissolve a whole lot of material. So we know that there are lots and lots of solids that when you add them to water, they will completely dissolve. Okay, so for example, if I were to take about a teaspoon of NaCl, sodium chloride, and dissolve that in a liter of water, I know that this reaction is only going to happen in one direction because, I just said one direction. Because I know that that solid is going to be able to completely dissolve in the water that's there, the 1 liter of water, and become aqueous, NaCl. So that is not the type of situation where my solid is reaching equilibrium in solution. That's not, because that goes to completion. There's no reverse reaction occurring there. But what I am going to present to you is a case where equilibrium does happen with solids in solution. So usually when chemists are talking about solids in equilibrium with their ions, we're talking about cases where the solid itself has a very low solubility in that solvent. So you may remember last year where we looked at solubility charts, and we were able to identify that certain anion and cation combinations created a solid, an insoluble precipitate. Well, as it turns out, those insoluble precipitates are actually really just slightly soluble, and even though we might not be able to see how much of it is dissolving, there usually is a few ions that will be able to be observed to be in solution. They're really, really tiny, but they are still there. And we'll be discussing this concept in a whole lot more detail and adding a little bit of math to it later on. But for now, what you need to understand is just the idea of it, that I can take a solid and I can try to dissolve it in water, and it won't be necessarily like the sodium chloride that will dissolve completely in a very, very small amount of water. Some substances, no matter how much water you add, will still only dissociate into ions to a very, very, very small extent. And so once that they do dissolve, the small number of ions that are present in solution, before any other PbI2 in this example begins to dissociate, we see these ions reforming the solid. So at that point we say that the system has reached equilibrium because the rate of crystallization of the ions is going to be equal to the rate of dissolution, or the rate of dissolving of the solid. Okay, so I'm going to give you an image to help you understand this. So when you first take a solid, and here's that solid, and dissolve it in a certain volume of water, then what you see is that if it's an ionic solid, then the ions will slowly be attracted to the water molecules, the slightly negative and positive poles of water. Water is very polar, and will start to be able to float freely in the solution. Now, if we're talking about a solid that's only slightly soluble, then not all of these ions are going to be able to be dissolved in solution before we start to see the ions returning and recrystallizing into the solid again. But we say that equilibrium is reached when we see that for every one ion that's going off and being dissolved, one ion is returning and recrystallizing into the solid. So that's what we're talking about when we talk about solids being in equilibrium in solution. So, some substances are really, really only very, very, very slightly soluble, in which case we don't produce a lot of ions in solution, and so we say that equilibrium is reached really quickly because the reverse reaction happens really early on in time-wise in that process. Okay, so the next one is gas phase equilibrium. The example I'm using, you can see, is nitrogen gas reacting with hydrogen gas going to make ammonia gas. So what makes this a gas phase equilibrium is that all reactants and products are in the same phase. They're all in the gas phase. Okay, so as it turns out, and we'll look at an example of this tomorrow, a demonstration of this. So if we were to measure the pressure throughout this reaction, each of these gases exerts its own partial pressure. And so as the reaction proceeds, we're going to see changes in the pressure based on which of these species are present. And so we can tell when the equilibrium has been reached because we'll stop seeing those changes in pressure and it will sort of maintain a constant pressure overall. That doesn't mean that there is no reaction occurring. It just means that equilibrium has been reached because for every molecule of reactant forming product, we have one product molecule reforming reactants. Not much to say there. Most of the work that we do in this unit will actually relate to gas phase equilibrium, and so at least at the beginning of the unit, so you'll be seeing a lot of this. Alright, so the last type of equilibrium that we're going to be looking at is the equilibrium that exists between acids and in solution and bases in solution. So you may remember from the tail end of grade 11 chemistry where we discussed weak and strong acids and the difference between them. So I'm just going to go over that to make sure that you remember it. You may remember that weaker acids and weaker bases, what defines them as weaker is the fact that they don't dissociate completely in solution. So, for example, all acids have a hydrogen ion that in solution is removed from the rest of the acid molecule and floats around freely. Now, in a very strong acid, you're going to see 100% of the acid molecules dissociate to release their hydrogen ion. However, with a weak acid, only a small proportion of hydrogen ions will actually dissociate and go into solution before hydrogen ions in solution rebond with the anion for that acid to form the acid molecule as a whole entity again. So let me explain this further. So, for example, here I have, this is your acetic acid, regular old vinegar. Now we know that vinegar is not a super strong acid, and we know that because if we spill some on ourselves, we don't burn our hand off. So when I take acetic acid and I add it to liquid water, what happens is that this hydrogen ion on the acetic acid will attach itself to a water molecule to form the hydronium ion. Okay, H3O+, which you may remember from last year. And that leaves behind the acetate ion without its hydrogen ion attached here, without that extra hydrogen that it lost to water. So if this were a strong acid, then I would see all 100% of the acetic acid molecules going on to release their hydrogen. And so I would expect to see 100 hydronium ions. And that would make it strong. That happens in a case of a strong acid. However, in the case of a weak acid or base, then we'll see that maybe only a small percentage of that weak acid or base will dissociate, and the rest will, before you start to see the reverse reaction happening. Okay, so really quickly, here's an example with ammonia. Ammonia is a weak base, so weak bases will accept protons. Okay, so my ammonia will grab onto a hydrogen from water to produce the ammonium ion and release hydroxide ions in solution. So if ammonia were a strong base, then it would accept all of water's hydrogen ions and release hydroxide. But in the case of a weak base, we see that only a small amount of ammonia molecules will accept a hydrogen from water before the reverse reaction begins to happen.